Okay, let's start the afternoon session. So the speaker of the afternoon is Professor Roemer from University of Warwick. And he is going to tell us something about the quantum engineering for compactively localized states in disordered Lieb lattice. So let's welcome.
So thank you very much for the introduction. Thanks to all of you for coming to this nearly last day of this two-week workshop. And I'd like to thank in particular Sergey, who isn't here, for actually inviting me and gives me the chance to work with, try this out, with Carlo, who you know from this morning, and Jir, on this topic. And I'm going to tell you, a very weird story. So we're going to get dirty. I'm going to look at what happens to all these lovely flatband states when I throw in this order in the mix. I'm going to look at it from a perspective of endless localization, maybe. And then as we go on, we sort of fall more and more in love with these flatband states, and we're going to reduce the disorder, and then actually want to do something with these compactly localized states. So that is the plan for today, and the plan has been written up in sort of these 5 papers. We don't need to look at them, but it's sort of fairly recent. And in many ways, that's less of a homecoming for me than it was for Carlo, but it's certainly homecoming in the sense of the flatband physics that we've done, because last time I was here was 6 years ago, and that was at the workshop on disordered systems. And in a few weeks' time, many of you will actually go there as well. It's no longer here, it's in someplace else then. But that's where I learned sort of first about the only excitement that is in sort of this flatband physics. And then it's quite good to be back now a couple of years to have to report on what we've actually done. And in case you don't recognize me, that was me. That may be a bit easier to recognize this gentleman over there. Maybe some of you recognize yourselves down here as well. Right, okay, so Carlo and also at the start of this week, Alexei introduced very well flatbands and flatband physics in these, let's say, quantum engineered lattices. So these sort of simple lattices that you make up yourself, and then try to find these compactly localized states and try to find the flatbands. This morning, Carlo spoke about the work by Seba Mukherjee, who showed you in these photonic lattices where we have these flatbands. For example, I think what he would call is the diamond lattice. Sorry, I'm not doing very well with this thing. So the diamond lattice over here, as well as, of course, the Lieb lattice over here. And you see that they can generate flatband states in the Lieb lattices, but then if they get the phases wrong when they send in their waves, so they don't actually have the phase, that they have an alternating plus-minus sign on these red Lieb sides, and they don't get flatband states, and they get dispersive states then. Okay. Furthermore, all I'm going to do is, if there's one thing that you remember, I'm going to stick mostly with Lieb lattices, and I'm going to distinguish Lieb lattice according to Lieb sites, which I will always have red, and so-called cube sites, which I always have blue, because that's going to make a difference for me, right? So Lieb, the red stuff, the exciting stuff is red. The blue stuff is the standard old cube sites. So, but these photonic lattices are not the only platforms where people have observed Lieb lattices. For example, already quite some time ago. Okay, I'm struggling. I should stand maybe on this side, but I don't want to. They actually made quantum wires, which they put down in a structure so that you can see localized, compactly localized states. This is again your photonic lattices here, but they also look at ultra-cold atom setups where you adjust the potentials so you get Lieb sites. When you have here, for example, the red lines is these experimentally observed flatbands. Okay, it's not quite flat, but it's pretty good. And here you look at atomic flatbands where they, and that's I think probably the most exciting of all of them, where they use scanning tunneling microscopy to pick up individual atoms and really move them around on surfaces. to then generate those Lieb lattices. And then they use scanning tunneling spectroscopy to change the frequency of the excitation and just move through the spectrum and see where is the dispersive bands, where are the flat bands. So this is really like Lego at the atomic scale that people can have a look at these Lieb lattices and look at these flat band states.
So how much large they can go, I mean, experiment? I mean,
well, that probably tells you already by just looking at what they've done here. This is not a huge Lieb lattice that they built up here, right? Yeah. So you see it's a 3x3 units are basically Lieb lattice that they can do. Okay, it's been a while. When was that? Look at this. So nearly 10 years. We can probably do a bit more, but it's, you know, it's hard work at the atomic scale, and it doesn't. When you, if I understand it correctly, and I'm a theoretician, I don't, but when I talk to the people that in Warwick do this, you know, you pick up, in this case, they pick up some chrome atoms, you pick them up. This wasn't an boring, but when they pick up atoms and then you move them somewhere, quite often you actually lose them, right? It's not as simple as picking up this gentleman's mobile phone here, right? When they try to do it at atomic scale, they pick it up and lose it, pick it up and lose it, pick it up and lose it, and then every dozen times or so, then now something sticks, and then you have to move it, and then you probably lose it. And, well, it's difficult stuff, right? So this is excellent engineering. I mean, you know, just think back 100 years time when they invented quantum mechanics, that you can actually pick up an atom. Just, you know, huge how far we've got.
Yeah.
Right. So okay. So
sorry, and then in this atomic thing, so how do they study some dynamics in these states, these localized states?
Well, this is what this picture is meant to show you. This should show you these Lieb states. Okay, now I can't. From here, it's too far away. So in principle, what is it? So you see at the edge, you see the center over here, you see there's nothing in the center, which should be the thing where there's a vacancy. And if you really look closely, you should have something where there's something in the center, and there's something probably in the center here, but it's not quite there. So if you look at that paper, it's not perfectly, but I mean, come on. They do it at the atomic scale, so. I think
what would be inside there? What are the waves which they run through?
Scanning tunneling spectroscopy, so it must be electrons which is just sending through there. Right? That's what it is as far as yeah. I mean, this is not light or something like that you send in there. Okay, so from the models that I want to talk about Lieb type models, and the way I'm going to construct them is a very pedestrian way, not the lovely way in which Alexei did it. So the way I think about it is, suppose you take a two-dimensional boring square lattice, and then you just put sides in between, which is, I think, one of the ways he said we can do it, right? And then I don't have to stop putting one red side in between. I can put two red sides in between, three red sides, and so on. So this is a whole family of Lieb lattices that you can have in 2D, and in 3D, of course, you can do the same. Again, start with a blue, simple cubic lattice, blue sides, and then put in the other guys in here. And when you do that, let's just quickly recap how, in the clean cases, how the dispersion relations look like, because later on, I'm going to put in a bit of disorder. I'm going to destroy those dispersion relations, and we see the leftover shadows of the dispersion relations. So it's useful to know how they would actually look. What you see over here is when you have this one side, you see we have the one flat band. Okay, I don't like that. I'll go mechanical again, right? So the one red side, you have the one flat band, the two red sides, the two flat bands in here dispersed. And then you can look at all these conditions that, again, Alexei mentioned, whether they can kiss, whether there are gaps, and so on. All this stuff basically works for this guy, right? Okay. And similarly in 3D, so here when you look at the L3-1 in our notation, so this is a three-dimensional Lieb lattice, but it has one red side, one Lieb side in between. And so the unit cell, which is given here in this light blue for the cube and the light red for the Lieb sides, you have four of these guys. You see you have three bands, but there should be four, and hence the flat band is actually doubly degenerate, so you can do the counting. And you see that in the other guys, again, here, 2 red sides, you have 2 bands, 3, you have 3 black bands, and so on. So you have a whole family of these guys.
Why doubling of the people?
Sorry?
Why double generated on 3 port?
Well, because you have a top band, you have a bottom band, and then need 2 more bands, and these are these guys.
Because I can think about 3 kind of, the CLSs are probably the same as the 2 case, right?
Yeah, we'll see them. Well, maybe we'll see them in a second. Yeah.
There are kind of like 3 times I can move because I have 3 planes.
Well, we find W degenerate.
That's the third.
I don't think that's the third. It's 4 atoms per unit cell, so you expect 4 bands, right? Upper dispersive, lower dispersive, only 2 are left.
So the third CLS, which I think about, can be presented as a combination.
Yeah.
Yeah, question. So anybody look at the lattice dynamics of those like generalized Lieb lattice?
No, I don't think so.
Yeah, that I found there will be many soft modes in the lattice dynamics. They call floppy modes. These soft modes with frequency very close to 0. It will be exactly 0 if you only consider the nearest neighbor refraction. Yeah.
Look, this extended models is something that we thought we came up with, but then we found a paper where people had done that before, but only for 2D. So I don't think anyone has done it in 3D yet.
Yeah, but these are not the lattice dynamics. It's the fixed lattice, and so the electronic.
What I'm looking at is fixed lattice dynamics. Yes,
Yeah.
you know, asking. So what? If you look at vibrational spectra there, yes, I don't think anyone has done it.
That would be interesting.
Yeah, it's probably something that
Yeah.
on my very I want to do.
Yeah.
Okay, question. You say you have n flat bands and n plus 1 dispersive bands. And that you can show, then you can show it.
Well, for us, it's an observation. I'm sure one can show it. I'm sure if Carlo would be asked to show it, he can show it.
Okay.
Right?
Yeah, I see. Yeah, I can observe it, but it's perhaps not very trivial to show.
I don't think it is that hard to show. I think you'll once we're done in 15 minutes, he has done it. He's not nodding, so maybe it's not changing. Okay, so here is an example of how these extended, how these compact delocalized states look like. This is the one that we've seen quite a number of times last week and this week. Now this is how it looks like when you have the 2 reds in between and the 3 reds and so on. You can actually do that. And then when you look at the 3D cases, then you put these compact delocalized states in combination on all the brackets, of course, and all the faces. So these are the ones that you're having. And now what we're going to do is we're going to put disorder as a potential on the on-side, on the sides, namely all the blues and all the reds. So we're just going to look at what happens if I put disorder in this, and it will be Anderson type disorder from a minimum to a maximum where the mean is kept at 0. And for me, disorder is always nicely captured in this Jackson Pollock paper, in case not many people know that. So this is something that we did in these first 2 papers. I'm just going to run you very quickly through what actually happens, because it turns out to be not that really interesting. Well, it can be interesting, but well, I should say differently. From the Anderson perspective, it is interesting. From the flat band physics perspective of people in this room, is probably not that interesting. That's why I want to run through it quickly. So here, what I'm just going to plot is for all these lattice types, I'm going to plot the density of states as a function of disorder. So the energy axis here, and if we were to go and look at, for example, at the normal 2-dimensional Lieb lattice, how does my density of states look like when I throw in lots of disorder, measure over average over lots of realizations of disorder? You see the flat band peak here at the center, the energy equals 0, as the decays very quickly, and then I have the lower dispersive and the upper dispersive band. And you see when I throw in the disorder, which is on the order of 2, and if you look at here, this was the clean case dispersion, which goes from -3 to +3. So once I have a disorder which is at the size of basically the strength of the bandwidth. All the internal structure has vanished and just had one broad band, and all these peaks have gone. And that's true for all the other guys that you see over here, right? So the disorder broadens those peaks, washes them out, whether they are peaks in the density of states for the dispersive or for the flat band. This just all goes away if I throw enough disorder. And the same happens in 3D. So here are the results in 3D. Again, I'm just showing the dispersion relation for the clean case, so the flat band in the center and the two dispersive, doubly degenerate flat band, two dispersive bands. And so we see this big peak became very quickly about 3, nothing's left. And this is about a width of 6 or something. Okay, so that means this flat band physics, when I throw in this order that doesn't distinguish between blue and red sides, gives you basically back what you would expect when you do normal Anderson, localization. And what happens when you do normal Anderson localization? Well, you get a metal insulator transition. You get at the transition divergent length scales. And if you were to plot the phase diagram, here energy on the horizontal axis and disorder on the vertical axis, you will get a phase diagram that roughly looks like this, that close to energy equal to 0 in extended states. At the band edges, you have localized states, and if you increase your disorder beyond a certain value, you have the famous metal insulator transition. And if you cut anywhere across this mobility edge, you have universal behavior, you get a universal exponent that's roughly this value of, well, actually this is the most precise value these days, 1.59. And what I'm plotting here is actually the wave function right at the transition. It's a critical wave function. And I'm plotting it just because you may have seen it, I think, appeared twice last week in some of the talks. This is what I put on Wikipedia 2004. So it's always delightful to see it appear in talks when people use it. Okay, these days we plot it slightly differently. So basically what we're just showing here, maybe as an explanation, we're just showing psi squared when it's larger than on average. So the white areas doesn't mean that there's no psi squared, just means it's less than on average. And then we're plotting little cubes. And we're plotting them with different colors along where they are in the set directions that goes into this board here, right? So red stuff is at the front, blue stuff is somewhere more in the back, and then in the end you get sort of the violet stuff in the back, the purple stuff in the back. And this is a self-similar multifactorial wave function right at the transition. Okay, so this is how it looks like in the normal Anderson phase. How does it look like in our case? Well, funny enough, doesn't look that different. So this is the phase diagram, normal Anderson. Here I'm doing it for the L31 guy. So in 2 dimensions, everything stays localized. We know in 2 dimensions, scaling theory of localization tells us without any interactions or without correlated disorder, everything stays localized. Happens for the 2D cases here as well. For the 3D cases, I get mobility edges. And the funny part for someone who does Anderson localization is these mobility edges look a bit strange. So this is the normal case. This one looks a bit funny. There are shoulders over here, very strange. But then the L32 guys, so the one with 2 leaps in here, you see that this was the dispersion relation. So what we had is we had a dispersive band in the center around energy 0, then 2 flat bands at plus or minus 1. What you see here is the dispersive band stays extended. The 2 flat bands, there's actually nothing that you see of those anymore. And then these other outer dispersive bands, which were gapped, you see over here, give you also a sea of extended states. And if you increase the disorder any further out here, everything is localized. So these are interesting phase diagrams that you get. And it gets even more funny when you do it for L33 and so on. So you can study these systems, look at those phase diagrams, and you can actually cut across the transition points everywhere that you want. And when you do that, you get basically the same kind of exponent back that you had before. Yes.
Yeah, question. What type of disorder? Site or?
It's on-site disorder, just potential disorder, random uncorrelated from minus W to plus W. That's what this W does over 2.
What it would be different if you change the type of disorder from site disorder to bounded disorder?
Yes, if you change it to hopping disorder, things will be different. It wouldn't change the universality class, but the way of these mobility edges will be different. Normally, this hopping disorder is weaker than the potential disorder. and you would find well, different mobility edges basically, and you would have to be inventive to get the right disorder, to get something that looks similar, but on a universal scale it's the same. So non-universal properties are different with just topic disorder, but universal ones are the same. So people haven't done it in any of that stuff.
Unless you take your chiral cases, some of your models are chiral, and for those you will actually preserve the entire function.
Well, for those you will get special states and energy equals 0, for example.
Preserve all of them. The rest will do what you described.
Yeah. You mean including, for example, this guy which has 3 or so?
But what I'm saying is, if you have a chiral model, which are the simplest ones where you have just one Lieb site which you add per one, then in this case I think you always have chiral flat bands.
Yeah, okay. So
it will survive under one.
If we were to do this, yeah. But basically, this is also known in the normal disorder model when you have off-diagonal hopping disorder, you know, that you get special things. You get the Dyson singularity in 1D, right? In 2D, you get something equivalent and you get some divergence and all this. So you would get a mix and then a marriage of both, basically. But again, I don't think anyone's done it yet, because unless you give me some experimental realization why I would want to do it. Okay, now this was the old stuff. And basically it was, if I put this order on blue and red sides, I'm throwing these things away, right, on the flat band physics. Now, let's look at some disorder that might preserve those flat bands. Namely, now we're going to put the disorder only on the original cube sides, and we don't put anything on the red Lieb sides. What happens then? That's what we're going to look at. Well, the first thing you can realize is that these states, because the wave function at the blue sides for those compactualized states is 0, they don't care about this disorder, so they will survive. So what Sergei just said happens in the chiral case, we now make it happen artificially, right? So we want to see what happens there. Okay, and something really funny happens. Remember the old phase diagram? Now this is the new phase diagram, and what I'm showing you at the moment just is the local density of states. Again, horizontally energy, vertically disorder. And if we look at this case, this is the two-dimensional situation, we see the density of states where there was quite a bit of weight here in the dispersive bands, and I've taken the energy equals 0 flat band out. So there is no flat band peak, I've just taken it out. And then you see by this disorder, if I increase my disorder, I basically push all my states closer to energy equal to 0. Furthermore, look at these numbers. I have huge disorder over here in terms of bandwidth, many, many times the bandwidth. I'm really killing this thing, but something seems to happen. And if you want to look at localization properties, we're going to do energy level statistics with consecutive levels, which is called R statistics. I'm just showing this to you here. Again, Alexei, I think we mentioned it before, but since you didn't explain it, I thought I'd show at least how this looks like. So if you look at the R statistics, you'll see this form of statistics when you look at energy differences and ratios of energy differences. We'll see in a disordered system, you get boson behavior, which is basically this line, whereas in an extended regime, you expect this GOE behavior, which is the green line over here. And if you look at the average across these distributions, you get two different numbers, namely in the extended regime, you expect 0.53, and the boson you expect 0.38. And hence, this is a number which allows us to distinguish between extended and localized states. So that's what we're doing in the next graph. So this really is now the phase diagram. Energy disorder again, and let's just look at L31. I'm going on this side, so you can enjoy the right side. So you see here, this was where my dispersive band is. And inside the dispersive band, the stuff is red, and red basically corresponds to this value that I have for my GOE ensemble. These are extended states, and all these extended states in the dispersive band, they get pushed towards energy equal to 0. Actually, we know it turns out that half the extended states get pushed towards energy equal to 0, and the other half gets pushed out here in the sea of Poissonian states. So half the energy from the dispersive band, half the states, they go towards energy equal to 0. They become more flat band-like. Remember, the flat band states live at energy equal to 0. By putting my disorder on the cube sides, I basically forced psi squared or psi away from the blue sides. I forced it on the red side, so half the guys do this. They go on the red sides, they change the energy, become closer to how the compactly localized states.
Yes, so just remind me, your disorder didn't break chiral symmetry. So the chiral symmetry is always preserved.
My disorder didn't destroy the compactly localized states.
But the
Chiral symmetry, no, the chiral symmetry is gone because the blue sides, you know, they have randomness on the blue sides.
Okay.
Okay. So basically, I take half my dispersive states, I make them look like compactly localized states, live on the, and half the other guys, I make them push out. Right? And this also happens for L32, which had the flat bands at ±1. I'm only showing you the positive half of the energy over here. So somehow I make my dispersive bands, at least half of them, look like they were compactly localized states. And I can actually see that this is what is happening. So I'm plotting here psi squared projected on the Lieb sides, which is the red colors, and psi squared projected on the blue sides, which is the cube sides. So you see psi squared close to energy equals 0 drops, particularly when I increase my disorder. Disorder 50 is the cyan color, so there isn't anything left close to energy equal to 0. So these guys that live on the cubic sides, the blue sides, they're gone. I've pushed them away from energy equal to 0. Whereas those that survive, I pushed them basically onto psi squared equals 1. I made them all look on the red sides. And the higher I make my disorder, the red guy here is 50, the better this gets. And this is not, you don't see any of the flat band states here. So there are no states at energy equal to 0. You see a few of those guys, but these are leftovers. They are not flat band states. There's something else, which, unless I get a question, I'd like to skip over.
So you mean there are still those flat band states which you just...
Yeah, I just don't show that. So there's the sea of flat band states up here, right?
How can you get metallic states out of your own? How can this R ratio give you something like?
No, what I'm doing is I'm pushing these guys away from the blue sides onto the red sides, and there's no disorder on the red sides, right? So I pushed them away, and now imagine
Those states are metallic states, right?
Well, those states have a average R statistics that is compatible with GOE.
Right.
Are they metallic or not? I didn't do a transport experiment.
They are somehow extended.
I would think they correspond to extended states. They live on the red sides. Yes.
That's a contradiction.
No, it's not. Why is it not?
Because you see that they become more and more compact localized light, but then they are not extended.
Well, look, the compactly localized states at energy equals 0 are degenerate, right? So any superposition of these guys is still a state at energy equal to 0.
But these are not exactly those degenerate states. These are still, they have
But they live on the red sides only. So I'm pushing all the stuff away from the blue sides onto the red sides by this choice of disorder. That's what I'm doing.
So basically, the state live on the red side, you have the compact localized state and plus
I have the compactly localized states on the red side as usual. They're happy to live there.
and then
But
plus.
then I made them lots of friends. I put half of the dispersive band I also moved on these guys. So what are we coming from? Basically, the idea is, look, I have all these compactly localized states. I can store stuff there, right? There's something that lives there. It's an eigenstate here, and then something that lives here. So I somehow made something that I could use as form of memory. When I put in this type of disorder, I make sure that all the other guys, the dispersive guys, that could take those compactly localized states and move them away, they just look like more compactly localized themselves. I gave them lots of friends. That's what I'm doing. Right. And we see outside, for example, we'll see outside is the opposite. So if the energy is large, you see the red stuff basically decays. The sides, the states that live on the red sides, they actually don't live at large energy, whereas the guys that live on the cube sides, the blue sides, they live mostly at large energy. So I moved them away. I basically separated these guys. And here you can see the participation number in a specific form, but that basically just tells you what you really should see. If I increase my disorder, the red sides that live close have high participation, so are extended. So it's not just energy level statistics we're doing, we also compute participation number. The higher the participation number, the more sites participate, the more you are extended. Let's say you see these red guys, they are close to energy equals 0, then they fall out, whereas the blue sides are less in the center. It's for these red guys. Okay, so that was the first idea. I put in a special compactly localized state preserving disorder. It doesn't exist on the blue sides. I'm sorry, it exists on the blue sides. And okay, forget about this. So we have this specific disorder that enhances these CLS-like properties. Even for the dispersive states, I enhance the Liebness of my lattice by putting the disorder on the blue sides. That's what I'm trying to do. You still with me? Some people know.
So how much 3D and 2D is different? Because up to now you show 3D, yeah.
I'm trying to go into 3D because
I mean, you up to, okay.
Because for me, 3D is when the metal insulated. That's an interesting case. 2D isn't that interesting for me. Right? Because everything stays localized in 2D. I'm going to slowly go back to 2D now. But it's easier to see what is happening in 2D. Yes, so it's easier to talk about these, where it's a little bit more complicated to talk about. But the results thus far were 3D results. I also have them in 2D, but they're not that interesting because stuff stays localized.
Immediately by
Sorry?
Immediately by disorder?
Yes. As long as I don't have correlated disorder, as long as I don't have interaction, as long as I don't have nonlinearity. So this normal stuff. So now we're saying, can we use this idea that we have these compactly localized state preserving disorder? Can we do more than that? And that's what we try to do now. So now I'm going to reduce the disorder to the bare minimum. So what I'm going to do is I'm going to have, maybe we'll stay on this side. I'm going to have disorder where I have binary disorder, 2 values. Namely, I'm going to put in, here, 2 disorder values, plus minus mu. So let's say this guy is the plus mu and the blue is the minus mu. So the light blue, this is actually not meant to be white, it's light blue. This is the dark blue is plus minus mu. And then on top of that, I have some little, again, disorder, which I try to indicate here by different sizes of these cubes. Again, only on the blue guys. And then I put the blue and the whites, I put it in random positions. So random binary disorder, not the full Anderson disorder, with a bit of changes there. So I'm reducing the disorderedness of my disordered system. Then I'm going to go for an ordered checkerboard. So I'm going to put the blue and the white at regular chess-like positions, blue, white, and so on. So just like a chess field. And later on, I'm just going to use a potential which is constant on just the blue sides. So I'm going to basically, now I'm just in an ordered system. Why am I going to do that? Because I want to show that this is still the same CLS enhancing property that I have by changing these on-site potentials. So here we see the first results. Again, energy and disorder. This disorder is now this mu split. And I'm plotting it for different additional disorder W. If I go back, because that may have been a little bit too quick, that this W disorder basically says the potential at all these guys here is slightly different, which are indicated by slightly different sphere sizes here. Okay, what comes out of this? So now you see this is the projection onto the blue sides. So you see that I'm plotting psi squared, again projected onto the blue sides, and you see psi squared for these blue sides close to energy equal to 0 is very low. So the blue sides, they don't live close to energy equal to 0, but the red sides, sorry, the blue sites have high entries outside for high energy, whereas the Lieb sites, they live close, the psi on the Lieb sites lives close to energy equal to 0, but outside for large energies, psi squared projected onto these guys is very low. So again, I made this particular disorder such that the dispersive bands that I might have now are really, half of them live close to energy equal to 0, and half of them live just far away outside. And by choosing this disorder binary, I get this basically this huge gap between these two flanks that I have. And if I add this to this, I'm getting 1, because of course sum of psi squared across the whole thing for a state has to be equal to 1. Okay, and this tendency stays even if I include more disorder in my binariness. So if I make this projection not as good, it just stays. The split between sites which are looking more like compactly localized or less, the split stays. Now I'm plotting the same thing, but not the psi squared. I'm plotting the participation ratio. So I don't just show you where are those guys. Do they live close to energy 0 or outside? I'm showing you those that live close to energy equal 0. Are they extended or not extended? And perhaps you see it here the best. Those which are close to energy equal to 0. Well, let's look at this guy for the Lieb sites. They have high participation numbers, so they are light red to yellow, whereas those which are dark purple, and this is dark purple out here, so they don't have high energy. Whereas, and I think I may have switched actually the colors a little bit. This is not the case for the blue sites. It's not so easy to see in these color scales. We tried lots of other color scales, but it's a bit hard to see because basically it's very close to energy equal to 0. So what I've done here is I'm showing you that not only do I get half the spectrum to look like compactly localized states, or to live on the sites of compactly localized states, I also move them there and they become more extended. So they're spread out through the whole system. Closed. There. Okay.
So how can you show that exactly half of them become more localized?
Okay, it's not exactly half. When we look at the spectrum, we find that it's half plus or minus one side. And again, I'm sure you could probably think about without disorder, when you just take perfect binary disorder on the checkerboard, you can probably do an analytic theory, but then you would find how many there really are. Okay, so this is now perfect checkerboard. Let's forget about this. Now I do this constant potential shift, and the only thing you have to really remember is that the split between states close to energy equals 0 and far away basically remains for all these states. So this engineering of the dispersive bands to look more like they live on the red sides works, and I don't need the full disorder that I did at the start. I just need some sort of cartoon form of disorder, and it still works. So why are we doing this? Well, basically the idea was these flat bands give rise to the compactly localized states. I would normally assume, and I've shown you before, that disorder destroys them. Now, can I come up with a way in which I can construct a disorder that doesn't really destroy them? It turns out this is pretty easy. I just need to make sure that at the Lieb sites where the compactly localized states live, there's no disorder. So now, if that is the case, then can I actually use these compactly localized states as some idea of sort of quantum memory? Can I store something with that? And that's what we're working on while we're here. And Carlo already told you this morning that other people have thought about this before. But basically, what these other people have thought about is they said, let's change the hopping integrals and then transport states by changing hopping integrals as a function of time. So this is a little bit like saying, I want to change my current locally, and then I'm going to get some transport out. Right? That's what many people do in transport experiments. They inject the current and see how much comes through. We want to do it slightly differently. Namely, we want to do it such that we send a pulse from the outside. In most of the experiments, what people have done is they prepared their two-dimensional Lieb lattice, and then they attacked it from the higher dimension from the outside. They injected compactly localized states or not. What we're now trying to do is we're trying to send in phases or pulses in the plane in which the compactly localized states live. Because later on, if, for example, we want to use it as a quantum memory, perhaps use it in 3D, we cannot just use this approach via hyperdimension. We have to actually be able to do it from the outside. So that's what we're trying to do here. And before we do that, I thought I'd show you a couple of pictures and movies. What happens when I let some of these compactly localized states just run. This is a perfectly compactly localized state in 2D Lieb lattice. It's an eigenstate, nothing happens, right? This is one where I change one side, and you see this thing sort of leaks out a little bit and then moves away. This is one where I must have done something else, which is now covered from over here. So it moves out. Okay, sorry, no, this is the randomized checkerboard. This was the ordered checkerboard, and this was just the cube shift. And the main point is here, going this direction, I reduce the amount of disorder, but basically these compactly localized states don't really care. Okay, here this leaks a little bit more than this guy, as you can see, but not really that much more. It's a bit more destructive. Okay. Now, let's see that these guys can actually store. And let's see if they start. So what I've done here is I prepared 5 compactly localized states. And then I perturbed 1. So this is not a compactly localized states. Instead of +1, +1, -1, -1, I think I probably just get 4 pluses. And you see the thing runs away. And you see how nicely it doesn't destroy any of these other compactly localized states. So this idea of using this as some storage device seems to be right. You know, I can have this information and it just, I mean, you wouldn't be surprised, right? It's an eigenstate, and the other guy is not an eigenstate. It's probably an energy which is not the same as the energy of the compactly localized state. So why would it do anything to that? But I still find it interesting to just see visually, right, how nicely this sort of the information in the 4 guys stays. So what have I done here?
But the memory is useful if you can like store, but also read and write. But here the case you can only store, so very useful of that.
Well. Okay, well, this is the first thing in the story, in the memory, is to have something that survives. These guys are survived. Next thing is, yes, can we do more with this? Okay, what have I done here? So this is again random checkerboard with different types of disorder. And here's rather weak disorder. This was this additional fluctuation disorder. And you see, so these states, they get out. This is very strong disorder. You see, this guy doesn't actually get out that much, which isn't that surprising either, because this is basically an Anderson localization condition. So here, this guy doesn't go out because the disorder is so strong that it can't really breathe, right? It's a little bit, it's localized by the disorder. Okay, but you were right. What I have to do in order to use these devices, I first have to be able to load them. You send the pulse and then load it. And once I have it, then I have to also be able to address it and basically clear the storage again. Okay, so it all works. Now, these are results that we did in the last 2 weeks. And what am I doing here? And Alexei and Sergey probably recognize some of the results. So what I'm doing is I'm now going back to one-dimensional systems, because we tried it in the 2D systems and failed miserably for a couple of months. So we thought before we do 2D, let's go back and do it in 1D. So we use these a quasi one-dimensional chain of Lieb lattices. This is what's called, I think, the cross stitch, and this is the diamond one. And here I'm giving you how these compactly localized states look like. This is, of course, from that paper that has been cited a number of times at this conference. And what I'm showing you here is, so this is the position in 1D, and this is the time by solving the discrete Schrödinger equation and discrete time steps. And what I'm doing is I'm sending in a pulse over here. And this is a carefully prepared non-dispersive pulse. This is a pulse which corresponds to one of the eigenstates of the system. I'm sending in a pulse from the other side as well, such that when these guys meet in the center, I put an absorber here and I can take the energy out. This is just a technical trick because I wanted to avoid having the pulse go through and by periodic boundary conditions come back and destroy what I have, or by hit parabol boundary conditions being reflected and destroy what I have. On top of that, I put 6 catcher 6 slight potential variations onto these sites. And then what as you see I'm generating is a state which a pulse comes, loads my information, and then this compactly localized state stays and lives and lives and lives and lives. So I've just answered half of your question. In order to be useful memory, I should be able to send in something and store the information. I've just stored the information that at these 6 positions, I want to store something.
So, but basically, when you're doing this, you come to the problem of like from 2D, you need to have the right.
Yeah, so what in order for this to work, what we have to do is we have to change the potential. We don't change the hopping integrals like the chaps before, we change the potential. So it's a little bit the opposite. So we've used the Ohm's law the other way around. We have to change the potential and then see what is the current that we generate. Right? We sort of, it's the alternative approach to the whole thing. But we're already chuffed that we get it to work in all these situations. Right? So this is already, this thing actually works and it stays. What if you don't do it rightly, what happens is that if you just put a normal state there, just a normal potential, you will have reflection and transmission, and the things will disperse left and right, and they just go anywhere, and you don't do anything. Right? To get to this condition that you get there and then they just live is actually quite interesting that you can really do that. Okay. Let's see, and I'm putting this out here, by the way. This is fresh to start a bit of a discussion. See what could you really do. So this is so now I'm at the end at 360 timestamps. I'm just showing you what the amplitudes are. And again, you may think these are very faint blue lines. Can you actually see can you see these very faint lines in the back? Just about, good. So you think these are very faint, but look at the signal to noise ratio. There's just blotting psi squared at the end. It's pretty good, right? This clearly something is here and nothing is here. I mean, this is an excellent signal to noise ratio. Yes, I have to drive it with a big bump, give it a big kick, but I mean, these guys stay there, which I think is pretty encouraging. Particularly, we were working Saturday and Sunday, and I think Monday you should have seen us with a big smile. This is now our Lieb lattice. So what I've shown up here, and now it becomes really faint a little bit, sorry, but what I've shown here is psi squared per unit cell, and in the previous one per unit cell. Now I'm showing it to you per lattice site. And this is the A sites, B sites, C sites, D sites, E sites. And here I'm showing you all the A sites, all the B sites, all the C sites, all the D sites, all the E sites. And the pulse that I'm sending in comes at the upper leg or the lower leg. It hits the B and D sites. And you see at the B and D sites, it is then absorbed. Nothing emerges from these guys. If you can't see the white lines, look at the final one. Nothing comes out. All the wave intensity goes to the A sites. That's not really surprising because they lie on the upper leg and they lie on the lower leg, right? So the pulse comes in, it's absorbed, but you have the 6 guys left and right on the E side as well. And on the C side, where I'm sending in nothing, somehow miraculously these guys emerge and they are there at the end. So this idea of storing information at these sites actually seems to work. Yes, it's only 1D, yeah. You know, have to do probably much harder work than 2D and 3D, but at least we got something out.
So the pools that you put in is like in 1D or permanent. So the pools that you put in is like.
So in 2D, you probably want to send in the pulse like this, 2 pulses that maybe crossing, and 3D 3. Or maybe just 1 big pulse might also work. We don't know yet.
So in the example that you show here, you send one direction.
In this 1D pulse, we basically send in. I mean, we just send 1D in this direction, right? And you see also these slopes are slightly different if I go back, because the slopes because the pulses I have to send in, I have to carefully select them to correspond to eigenpulses. If I wouldn't use eigenpulses, then I would just normal pulses, they would disperse. They would just immediately go. All right, so this is really quantum engineering to make the thing do what I wanted to do. Okay, where are we? Well, we're at the end. So I told you a little bit about Lieb models, which here at ground zero of Lieb model physics, probably I don't have to do. we talked about some of the fundamentals. So the first part was understanding what happens when I have CLS preserving disorder. Next part was engineering. Can I select my disorder to be even better in terms of CSL preservation? And lastly, the last part was control. Can I use these Lieb guys to store some form of quantum states? With this, I thank you very much for attention, and now we can discuss.
Questions? Yeah.
The new mentioned CLS preserved said that it's important to add a disorder at sites where the CLS function is zero. But out here is like
No, not where the
CLS.
I put this, yeah, okay, you're right. I put at the blue sites where there's compactly localized states wouldn't normally live, so that it's not effective.
And I think out here is like for the other like lattice sets such as complementary lattices, CLS takes part in like every cell of the lattice. And is it impossible to add a disorder to such systems such that CLSs are preserved?
Well, if you would want to use those for information storage in the way we're doing it, I would say that would be a very bad candidate, yes.
Yeah, please.
It's just.
Could you speak loud?
Yeah, I can add this one.
Say it again, please. Well, I can't, Alexei can.
All states? All states of the function?
No.
Half of them might work, but all of them. So basically, you can always add, let's say, rule such that you preserve CLSs, but since in carbon they are not orthogonal to each other, you overlap. They are even linear dependent, but they are overlapping. You can basically preserve every second. You can do that. The other ones go to, but all of them.
But all of them say that.
Okay. So that was your question. I mean, a comment. Okay. Fine.
I have a question. So you want to store quantum information, but the way that you show us that you can only like create the precise square, but not the face.
So I can create.
Like the way that you drive the system to create the information, you can only create the precise square and the amplitude, but not the phase, right?
Ah, this is the eagle-eyed one. Very good question, really.
Because if you want to have quantum information, the phase is also important.
Well,
Here I see.
maybe, okay, depends on what you want to do with my quantum storage. If you want to, I'd be happy to just store where these guys are. Right?
And then
so I'm happy to use my quantum memory for classical storage.
Okay, it's fine.
You're saying you want to also store the phase here, right?
Make it more ambitious.
See, one of the problems that we're dealing with and don't know the answer yet is remember that the state is plus, minus, plus, right? So 1, minus 1, 1. I've just shown you that I'm counting apparently 1, 1/2, 1. Right?
But you have the like classical signal.
Yeah, so classically I can use it as storage. All I'm saying is there could be that I'm missing some phase information. It could be that I'm not actually storing a CLS. Can I repeat the movie thing, Carlo? Okay. You know, I mean, I'm white hair and so I know a movie called The Fly with Jeff Goldblum. Do you know that movie?
Right.
Yes.
The Fly. Jeff Goldblum invents something that takes you apart here and teleports you to here.
Okay.
And one evening when he's very drunk, he hasn't tried it with humans, he has tried it with I don't know, with cups, he gets in the thing himself, transport himself, but unfortunately there's a fly in that
yes,
space.
yes.
So he comes out as a fly, basically, right? And a little bit, that could be our problem. What we've done here is, I told you that at the CLS sites, I'm storing something. But I was hoping I store a CLS, but this 212 suggests to me I might be storing a fly. I might not be storing a CLS, but there could be another state that is there. And we haven't resolved it yet. So we should project this onto CLS states, which we tried, and it seems to work, but maybe that's just because we made a convenient mistake in the code. My mistake at this stage.
I think like if you have like two deep atoms, then you have the COS state for each side become like degenerate. In this case, it's naturally to believe that you can print quantum information because the inverse space is one. Like the dimension of inverse space is bigger than one. In this case, you can use COS to store quantum information, but I just don't know how to print information.
Well, so the question is, who decides at what of these 6 positions you want to store the information?
Yeah.
And that is something that we would still have to do from the outside by saying, I want to store at this position by changing the potential slightly here. That's what I want to store. Okay, yes. But again, if you want to dream, you could think about sending in a pulse and another pulse, and then these two meet with a high amplitude, then you actually store it, and not before, because there is also a bit of a threshold here, how much you send in.
More questions? If not the case, let's thank Professor Roemer again.